Welcome to the Building Doctor Show with Jens Johansson.
Hi, everybody. This is James Jenkins with J2 Building Consultants. I'm standing in for Jens Johansson today on the Building Doctor Show. What you're about to watch has been pre-recorded, but I want to assure you there are human beings on the other end. So when we're done watching this, myself and our principal, Jim Kessler, will be on to answer some Q&A and interact with y'all. So without further ado, enjoy, and we'll see you in less than an hour. Hi, James Jenkins here, Senior Project Manager and Engineer in Training at J2 Building Consultants. I'm going to be standing in for Jens Johansson today, hosting the Building Doctor Show. So hang on your hats and let's go. Our producers are going to be monitoring the chat, so as always, be sure to put your questions into the Q&A box and we will answer them at the end of the show. And we have a couple of disclaimers. So this show is free, so please put away your credit cards. We're not selling anything. This show is for educational content only. We're not giving legal, financial, or engineering advice, and I'm not a medical doctor. We're just people on the internet trying to help you run your building better. We've helped thousands of people with their building problems and have seen what worked and what didn't work when it comes to restoring and running condos, and want to share that with you in hopes that it benefits you. So yeah, stick around for live Q&A at the end. We'll answer as many questions as we can in the hour and then add the rest to the next show. So if you have a more specific question, stay tuned for a link to the schedule. You can schedule a free one-on-one call with me. Brooke's going to be monitoring the chat. I'm going to go through the Q&A panel at the end of the show. So be sure to ask us your questions. So today we're going to be talking about beams. What are they? What are they used for? What sort of tools do we use to diagnose issues? I plan on covering an array of things, so I hope your eyes don't glaze over, but I'm really excited to be discussing this topic. So beams in general, probably the most important structural member that we deal with in our industry, in the construction industry. I guess a beam, right? This kind of looks like a beam. I think a beam is a long, slender structural member. It has a uniform cross-sectional area, and generally a beam is loaded perpendicular to its axis, right? So several things serve as a beam. I'm sure you've heard terms like joist or rafter or stair stringer, right? All of those serve as a beam. Beams are supported in a handful of different ways, right? We have simply supported beams where there's just a support on either end and a long beam goes across. We have cantilever beams. They are fixed on one end and free on the other, and so on. So in our industry, right, as building envelope consultants, primarily we're going out, we're doing visual observations in the field, and we're looking at decks, we're looking at stairs, we're opening up some wall cavities and assemblies like that, roof assemblies. So yeah, we're looking at beams that support joists. We're looking at rafters that support roof loads. We're looking at stair stringers that support stair treads. So a whole bunch of beams. Let's talk about materials of beams, right? So we're in the Pacific Northwest. We have timber. We're in timber country. So primarily we're dealing with wood and the exterior application. We see, you know, you guys are probably familiar with saying pressure treated. Well, we like to say preservative treated. So yes, the wood that you see has been treated with a preservative. It has been run through a machine and striated. So it's got all these little divots and dashes inside of it. And then they soak it and push material into that lumber. The species of lumber is very important. So we talk about Douglas fir, or we talk about hem fir, or we talk about Western red cedar, right? All these different woods have different strength properties. So primarily when we're building houses, we're using Douglas fir as a lumber to frame. It's strong, it's plentiful in this region. On the exterior application, we talk about preservative treated lumber. That's a different species. You probably didn't know that. We use hem fir for the preservative treatment because it actually absorbs the treating chemical more so than Douglas fir does. So with that, the hem fir is actually a little bit less strong than the Douglas fir. So as engineers, we need to be thinking about those strength properties when we implement designs and repairs, and we have to be thinking about the strength of the materials that we are using to get your project to the finish line. So fun little fact there. There's also concrete, right? Reinforced concrete beams. We see that everywhere, especially in parking garage structures. And then of course, steel. Steel is, strong. It's relatively inexpensive. It's easy to get. So yeah, we uncover a lot of steel, but Pacific Northwest, it's timber country. So we can talk about some of the ways that we want to investigate, right? So primarily we get called out to a project, and what's our number one tool that we use? It's our eyes. So we look at something, and based on the number of properties and places that we've worked in our background in construction, engineering, and architecture, we have a pretty good educated eye and can pick up some things that you might not normally see, whether that be staining or a little bit of difference in texture. Maybe something like we might look like peeling paint or bubbling, but it's actually on the wood surface. So we can kind of hone in and focus. And then, we have an array of tools that we use to kind of poke and prod around, right? Whether it be a pocket knife, or little hooks, awls and pokers, fun little prying tools. I'm sure you've seen gens using a pencil or even a pen, just poke it with a pen. But these are great little indicators to kind of feel around and see what's soft or firm or whatnot. Aside from some of those hand tools that we have some other fun, cool, technical tools. We have, moisture meters, devices like this, non-invasive moisture meters. So you can simply hold these on a surface and they're going to tell me if it's wet or not. We have some invasive moisture meters that have, little pins that we can poke into wood, and it tells us if something's wet or not. And when we see things are wet, right, that's going to lead us to tends to lead us to the damage, right? We're following the water, we're following the leaks. We have thermal imaging cameras. Now, this isn't a water detector camera, right? This tells me a change in temperature. So I take that information and I correlate that with an assumption that there might be water or something. So these aren't tools that say, I'm a damage detector, right? They're measuring content, they're measuring temperature. And then we take that information and we help reinforce our assumptions, basically. We have data loggers that we can place in crawl spaces and attics and areas, and we can record temperature and moisture content over the course of a day, over the course of a week, over the course of a month. And then look at those spikes, those peaks and valleys on moisture content, and determine if there's ventilation concerns or moisture concerns. We have relative humidity sensors, right? So a fresh slab of concrete, we're going to be putting some sort of a coating over the top. How do we know when that surface is at optimal moisture content to be able to take that manufacturer's coating? We have to know the relative humidity. Well, we can place these sensors inside of a slab and then come take periodic measurements. So there's so many different tools we can use to help us find moisture content or temperature or things like that to help us kind of get to the finish line on that, on projects. Yeah, so kind of, burn through basically some of the tools that we use. There is no magic smoking gun, right? We have an assortment of tools in our toolbox, and we use these at different, sometimes we lean on the technology. Sometimes we just lean on the poker, and our vision. So let's take a look at some video, just some fellow J2ians out in the field looking at some situations, and maybe we can kind of talk through them. So I see one of our engineering staff, Stephen Ting, out in the field, and we can see a deck here. And basically that deck's got a waterproof coating on it, and we're looking at a beam. He's basically leaning his ladder on a beam that's supporting some framing members. So we can see Stephen is using, the trusty awl, right? It's a sharp poker, and he is probing the beam, and you can see that just that awl right there embedded about 2 inches into that member. So he's basically looking around. You're going to see a column, a vertical column there. It looks pretty damaged. I don't know if you can see kind of the change in texture there, but these are generally going to be the locations, right, as they sit and absorb water, deteriorate at an accelerated rate, and that's primarily where we're seeing damage. This beam here towards the end. So these are indicators that we use before we break out the big guns, so to speak, to go out and take a glance at a structure. We're looking high. What's above? Are we supporting 3 stacks, like in this instance, and a gentleman that you see there? So these are some of the things that we have to do in an investigation to determine, hey, is there time to help develop a scope, or do we need to implement some temporary shoring, right? Temporary shoring is going to be a structure that supports this structure in the interim while we help develop a scope. So that's a big facet of what we do at J2, aside from just going out and doing our observation, right? We're determining if there are life safety issues. And if we determine that there is, we need to come up with a plan relatively quickly to ensure that we have a safe community, right? And the people are safe in the interim while we're developing that scope of repair, that permanent fix. So yeah, you can see some of the good indicators on the side of this beam is the separation. You can kind of take a look at that without poking it, probably think there's probably some moisture issues here. So, that's where it takes an educated eye, but, he's got this wall opened up. You can see that there's some gypsum wallboard, or drywall, if you guys want to call it that. A lot of times you'll hear GWB, right? It stands for gypsum wallboard, and it's very brittle, and the paper face is deteriorated. So there's a lot of wrinkling on the weather-resistant barrier here. So really, there's been water leaking into this wall cavity for a long time, and now you're starting to see, it wreak havoc on the structure. So a comprehensive repair plan is going to have to be implemented here. But, this is some of the preliminary work that we do to try to determine the condition of this particular structure, right? So, the level of decay or water damage that you're seeing on this member is probably going to require a little bit of shoring, which is where we would probably stick a post or something underneath it just to provide it some support. While we're waiting for a more comprehensive repair plan. Some of the methods that we use to help protect the wood structure, right, is this flashing metal that you see on top. It's a good effort, right? But generally where we see the breakdown in this material is the integration with the wall cavity. So this coping metal that you see here looks like it just terminates and butts directly into the wall, rather than having a flange that wraps around and integrates with the weather-resistive barrier system. So as envelope consultants, we specialize in those weatherization details. Those are the types of details that are important, that buy you that long-term repair, as opposed to just putting something on there, running a bead of sealant, and then allowing the UV rays to break that down and then have it be a leaker, in a relatively short amount of time. We want to, present you with 30-year, 40-year, 50-year fixes. Do it one time and then enjoy your property. So, while it might make sense and be more cost effective, on the front end to just, repair something, put a little sealant on it, really coming up with that comprehensive repair on protecting the structure, is really the most efficient way to go. So a lot of times what we'll find on a deck structure is what's known as a soffit, right? And a soffit is basically covers up the ugly framing underneath. So it's an aesthetic feature. Sometimes we utilize soffits as for fire ratings, right? We can use gypsum to buy us a certain level of fire rating, but it covers the framing. So in an investigation like this, where we obviously have some concerns with water, we have to remove the soffit and then look at the underlying components and see the damage. So we will, get underneath the deck frame, remove the soffit, and then take a good look at the structural connections. Now here I see, there's fasteners that are missing on a bracket. Notice the deck sheathing, how they can bend, basically you're in danger of stepping through this deck, right? So the level of water damage here is basically, going to require some shoring. We might have to put a piece of plywood up on the surface to ensure that the owners don't step out and step through that deck. Or we might have to prevent access to that deck, right? Put a piece of plywood over the sliding glass door. So these are means that we have to take to ensure that the people stay safe while we're developing that comprehensive plan to, in this instance, looks like replacement is going to be the way to go. So we notice that these joists, right? And these are acting as a beam, right? That's the magic word of the day. We can see that the amount of water that has been coming into the structure, and basically this beam is wicking that water and staying wet. We have significant damage on the ends. And this is the most critical part of that structural member. Which is where we tend to see them fail, which means, repair is probably not an option here. We're going to be looking at total replacement. The indicator on the color of the sheathing, this is where a moisture meter is going to come in handy, because there are times when we're opening these kind of decks up in August, right? So while that looks saturated and its damage is apparent, right, it's bone dry. So, those are some of the tools that while we're taking pictures, right, a picture doesn't really tell me a story. That particular stain here could be bone dry. So we'll use our tools, to be able to relay that information in our reports. So just another reason why, we lean on an assortment of things to get that information. But yeah, more staining. So obviously there's been, water damage happening and occurring on the structure for a long time. So here's a project that probably don't need a moisture meter on this one. LOL. So we're basically probing this beam. This is a landing beam taking stair stringers, supporting stair stringers, and literally this structural member is full of water. So, sometimes video is probably the best form to be able to relay this. As a picture here, I see wet, but this could be active rain or water. But we had to record this one because this is something that you don't normally see every day. So we had to implement shoring, and shoring is basically just a temporary structure to support a structure that can no longer support the code required loads, or the loads that it was designed or intended to support. Literally a very juicy beam, to say the least. Another form of shoring, and they're actually trying to jack up a beam that is deflected. But this is a good explanation of, hey, we don't want to just rip something out and start fresh. We don't want to, how easy would it be to just tear out the whole thing and rebuild it? It's not feasible. Right? There are budget constraints, just the impact on the structure above. There's people that live here. We would have to relocate people for who knows how long to completely do an overhaul on the structure. So what we will do is implement a shoring means, right, to ensure that this long beam, I guess, a term this would be called is actually a girder, right? A girder is a large beam, and this is generally supporting large floor loads, right? So this is underneath the living space. You have a giant girder acting as a beam, and it's picking up an immense amount of floor load. And as I play this video, you're going to see the amount of the deflection, this wedge here, right? So basically this girder has settled, and now we have a huge dip in the floor, a huge belly. And you can see that these guys are trying to basically jack up this girder and recover that deflection. So it's a timely process. As I speak through this, we'll be able to kind of see that gap get shorter and shorter. But really, pretty primitive tools we're using here. There's a bottle jack. There's one. There's two. We've got a couple of steel posts under there just in case the jack fails. Right? So this structure is shored at the moment, but what we're doing is basically trying to recover deflection, and they're just inching up on either side, slipping another block in there and continuing the process. So It's not rocket science we're talking about here. It's slow, it's steady. It's not using, $1 million tools, but it takes good judgment and experience, right, to determine that we can recover this as opposed to having to rip the whole thing out and replace it. So let's get a little bit further down here and notice they've already closed that gap up. If I could do time lapse, it'd be really cool, but it would probably give you all motion sickness. But anyway, yeah, this is a classic project where we implement bottle jacks to basically recover the sag, and then they can reframe this deck. Everything's straight. Hopefully, there's not too much cracking above. But yeah, they're lucky. They're lucky on this one. They're able to recover it. So thumbs up to the team. Yeah. So once they've recovered that settlement, what they're going to do is basically implement a new bracket for this beam and probably post down and add a footing, right? So that way we have a simply supported beam, right? So it's mainly supported at this concrete foundation wall here. So yes, when all of this is done, you can see these poles and posts will be removed, and the beam will be serving its purpose as it was originally intended to do. So offhand, it doesn't look like the beam was water damaged. It looks like the support failed for the beam or how it was attached at this foundation wall. So they were able to basically put bottle jacks underneath it, recover that settlement, and then what we'll do is actually, insert probably a supplemental pier out of concrete with a post. And that's a relatively inexpensive fix to pick up such immense loads, right? There's an incredible amount of load on this beam or girder, if you will. You notice that they're inserting a plate inside. So basically, the bottle jack has about an 1.25 inch diameter cylinder, so it would literally push up into that wood beam. So they're inserting a steel plate to help kind of distribute that force and not damage the face of the beam. And they continue. It's a slow process, but it's a tried and true method. Just amazing how much force can be applied through a little bottle jack. Thousands and thousands of pounds. And they see they've recovered that settlement. You can do a little step down memory lane. See where it was before. So it was an incredible amount of work, but they got it. They got it to the end. There it is. So that's a success story. It probably saved the client a lot of money. You can only imagine if they had to replace this whole entire framing assembly. The cost implications would be pretty high. Yeah, so I can sense that maybe this is like me shooting a fire hose of information and you're trying to drink it all in. If you want to dive into the weeds with me by any means, you can reach out to me. We can talk about beams. We can talk about stress wave testing. We can talk about the weather. I'm James, and my phone number is 503-379-0717. Yeah, so I will be placing my contact info on the screen. So if you want to reach out to me or reach out to Jens to discuss anything, feel free to do so. Look forward to hearing from you. And then moving on to the exterior of a project, here's one that we were able to actually do some video in the rain, so you can get a feel of the actual. Again, I was talking about that Soffit material, right? So a Soffit tends to be a good, it hides a lot of damage a lot of times, but there are indicators, right? So we can see the bulging here. We can see some of the discoloration, see that brown staining right there. So that's a good indicator that something's happening. And oh, lo and behold, right? We can just see,
There's a gypsum wallboard there, right? The drywall, that's for a fire rating, and that is just like powder and crumbling. And then you can just see the sheathing, right? That is basically your plywood decking is just, it's gone. So in this instance, what we would do, right, is stop recording, and we would want to implement some shoring underneath that, just to provide the support that we need to ensure that the occupants are safe. And that also gives us the time we need to develop that comprehensive repair and implement it. So, assess, we uncover damage that we constitute as a life safety concern. We immediately want to implement shoring there. So that's our left, right, uppercut. Some more video of literally that member being saturated and full of water. Notice how dry we are above, right? This isn't somebody pouring water or a hose turned on. This is the inside of a beam, and it is just draining after being impacted with water. So I will say that's not the norm. I don't see that every single day, but when we do, that's something that Okay, now I'm transitioning to stress wave testing. So one thing I want to transition to is some of the non-invasive forms of investigation that we don't do all the time, but we can do, right? It's all about having tools, and when we use them, it's job specific, it's project specific. So one form of testing that we did some research on is called stress wave testing. And stress wave testing basically consists of some instruments, okay? And there is an accelerometer on one end and an accelerometer on the other end. What is an accelerometer? Basically, a signal or a noise or an impact is picked up by one. Think of it as a microphone, but it doesn't project noise. It just records that impact. And then basically that signal is sent across a material, and the second accelerometer picks it up. And then the instrument tells us the time it took for that signal to hit point A to point B. That's it. So these instruments aren't damage detectors. They aren't water detectors. They are simply sending a signal on one end and measuring the time it takes for a sound to move across a material. In this instance, the material, you can probably guess it, is wood, right? It could be plywood. It could be a beam. It could be, we're using wooden substrates. So there's been research done, right? The U.S. Department of Agriculture has documents where they've actually, done testing to certain species of wood, and they've logged those numbers for, Douglas fir, for hem fir, for maple, for every species of wood. So the thought is, can I come out and can I look at a structural member, a wooden member, and without sawing it in half and taking a look at it, without poking it with a stick, without hitting it with a hammer, and beating it, is there a device that I can use to help me determine if this wood is damaged or degraded, or maybe the structural properties have been reduced due to, exposure or what? So we basically rented some equipment and did some lab testing with it. So I want to talk about stress wave testing. So what you're seeing right now looks like a little bit of a lunchbox, and that's basically the device that's going to give me that number, right, that I'm working with. So this zigzag metal device is known as a trombone clamp, okay? And what you can see is there's basically, it's portable. It's a portable device that I can take out. I can set up sawhorses in the field, and I can lay it on a piece of material. So in this instance, you see that there's oriented strand board, right? You're probably used to hearing OSB, but it's a sheet membrane, a structural membrane. We use it like for wall sheathing, for roof sheathing, for floors and whatnot. So the idea is I can lay this trombone clamp on this substrate, use a pendulum hammer, which you'll see, to send that signal through the accelerometer. And then the time it takes for the other side to pick it up is then projected on the lunchbox. Right? So the logic here is, can I record the measurements on a good brand new piece of plywood or substrate? And then what are my readings going to do when I get on something that's more damaged, or, you know, water damage, deteriorated, has insect damage or whatnot? So that's the thought process behind this testing and what this device will do. So, you know, imagine if I took a piece of plywood sheathing off of a building out at one of your properties. Imagine if I sent it to a lab and they told me what the strength property was, that a normal piece of the siding, you know, would have a certain strength value. And then this particular one off the site was, you know, 40% reduction in its strength. Well, now I can use this accelerometer, right, to measure what a piece of siding with a 40% reduction in strength is. And then I can go to other pieces in the field and go, well, that's, you kind of see where I'm going with that? So that's kind of the logic behind this particular instrument. It's portable. I believe they use these on the factory line when they're actually manufacturing plywood. So as fresh sheets of plywood are coming off of the line, they're basically measuring it and making sure that they're within, you know, what they're constituting a good number, basically. Yep. So now you can see I have a sample that is a water damaged piece of wood. And then what I wanted to try to prove is that based on the orientation of the board, right, there's a strength axis. So a vertical piece of plywood versus a horizontal sheet of plywood is going to have different readings. So yeah, the audio is going to explain exactly what I'm talking about.
You would think with OSB it wouldn't matter on the orientation because all the fibers are oriented in a hodgepodge here, but really I am finding differences when it's oriented parallel to the APA stamp on the back and perpendicular to the APA stamp on the back. You're comparatively testing here. There are ways to calculate properties such as the modulus elasticity of the panel or material that you're testing. But right now I'm just trying to take what I'm calling a good piece of OSB and gather that value and then compare it to other pieces that have moisture damage and organic growth and decay. So establishing my base values, I do have some pieces that I'm calling good, and I do have some evidence of the stamp direction. So parallel to the APA stamp on the back, I'm getting ranges from about 100 to 110. This one, I got a value of 108. In the same sense, when you go perpendicular to the APA stamp, I'm getting readings that are anywhere from about 135 to 145. So those are kind of my values I want to see on a good sheet of plywood. Here's a piece that I found that actually you can see that the orientation of the APA stamp is in this direction. So I would want to see 100 to 110 here, and you can see I got a reading of 135, an elevated time it took to travel across this thing, meaning that it took longer, meaning an elevated level of deterioration or decay. This is a piece that ranges from pretty good on this side all the way to severely decayed or damaged. Unfortunately, I don't have a stamp on the back, and I tried to use these lines to orient it with a good sheet, but really with this factory edge here, no matter which way you orient it, these lines could line up. So I'm actually going to just use the values to kind of try to guess which direction this orientation is going. And you'll see that the numbers are really, really, really elevated in severely deteriorated areas. So I am going to guess that we're actually going parallel with the, perpendicular to the APA stamp. Regardless, a 130, 140 would be normal. I am getting a reading of 150 here, but this probably does have a little bit of deterioration happening. I mean, as much moisture that's been in this board, you know what I mean? I think that 155 is kind of the best side of this piece, and it kind of starts elevating as I work towards a deterioration. So regardless, here's a comparative test. 155 on my good side, 156, 185, we're getting a little spongy, maybe like the threshold of we want to start tearing the sheet off and replacing it with new, and then all the way up to 230. And I can definitely push a probe through this. This is definitely what I would call a failed material. So anyway, that's what I've been able to gather with this material. I'm hoping to do some other types of panels as well, but this is what I have for now. So that is the trombone clamp.
Yeah, so a trombone clamp is going to be used on sheet goods, plywoods, and sheathing, right? There's a different instrument that we use, and it's so basically stress wave testing, that concept of measuring a signal from one side of an accelerometer to another, that we're timing it, has a couple of different instruments we can use. Yeah, so the trombone clamp is going to be for sheet goods. This is the table clamps. This is another very similar, where you have, you're clamping a device on one side of a panel and you're clamping a device to another side of the panel. There's an accelerometer. There's accelerometer number 2. There's a pendulum hammer. There's a pendulum hammer here. You drop it and it sends that signal across, and then I measure it. Now, a beam, we have a stress wave hammer. Okay, so how do we do beams? Basically, there's the same lunch pail that you're talking about. So I'm just picking up a number, and I have, let's see if there's a picture of it here. Yeah. So basically, we have the hammer in one hand, okay? And then just what looks like a doctor's stethoscope in the other. And they're both connected to leads, right? So you have accelerometer number 1, accelerometer number 2. And the thought is you hold these on one side of the beam or the other, and then you basically record the measurement between. So if you can imagine the time it takes in a good piece of wood, tight grain, no knots, the path of least resistance, right? It's going to be a very low number, short number, because that signal in the snap made it from one side to the other. As the wood fibers start to break down, as we start to see that water damage, as there's big knots and checks, that signal has to work its way around the resistance to get to the other accelerometer, number 2. So we can correlate those numbers, right, with a quick, good, fast number as quick, good, strong, undamaged lumber, right? As we start seeing that number increase and increase and increase, right, we can start saying, oh man, there's got to be something going on in here. I'm encountering damage or something that's, so it's not telling me that I'm a damage finder. This is it. James, you have a hollow post. But I know that the time it's take to travel from one accelerometer to the other is increasing, right? So there have been studies, and there is documents. Okay, so the United States Department of Agriculture has a manual that they've created, right? So in this, they've actually done and created the data that helps us with stress wave testing. So they have typical stress wave transmission times, right, for non-decayed Douglas fir at a certain moisture content. So there's information and there's numbers and indicators that we can use, by, USDA and entities like this that allow us to basically take the information that we collect in the field and then apply that to our findings report. So an experiment that I did on a 6x6 pressure treated or preservative treated post, right? Now the cat's out of the bag, right? The post is hollow. We can see that. So, like I said, the cat's out of the bag. We know that this thing is hollow, but imagine if this thing was standing 12 feet tall vertically. To the exterior, it looks fine. It looks solid. I hit it with a probe. It's, wow, this thing's solid. It feels solid. How would I know, other than sawing it in half, if it's in fact this damage like you're seeing here? Well, so that's where I use the stress wave hammer. Now, if you can imagine, okay, what you see right here, this square, as the cross-sectional area of this beam, okay? Imagine green is good, right? And as we get darker and darker toward the brown, right, that's leading to more decay and damage. Now, I'm going to ask you, you can see these little points here, 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 here. These are areas where I tapped the hammer and took a measurement, okay? So if you notice, the four corners look pretty green and good. Now, green for me was a relatively lower number, right? So I was in 900 to 1,000. And you can see on my corners, right? Green is good. Look, we're good here. We're good here. We're good here. We're good here. What happens as I start recording numbers getting closer and closer to the middle of this post? They start getting longer. That resistance is taking a longer time for that signal to get to one end to the other. Oh my God, 3,600. Wow, that got really long. Well, look, I have a complete void here. So that signal hits here, has to go down here, travel, get up here, boom. So that's the concept of stress wave testing. If I can try to visualize it to you guys, is, you know, I can go with a hammer, a stress wave hammer, and tap on a beam or a wood post in the field and not drill into it, not cut into it, not damage it. And I can tell you kind of with numbers, with an electric signal, right, what the cross-sectional area of this post is going to look like if we in fact cut into it. Now, do we do this on every single project at J2? No. But the thought was, can we demo this material and how would we utilize it if we had to? And this was just a great opportunity to be able to kind of experiment in our lab and show you, you know, the proofs in the pudding. So yeah, it was a lot of input. So here's my table value over here where I had to basically take a measurement, you know, rate the material and then record, right, and correlate that into an Excel spreadsheet. But I thought it was pretty cool. It's a good diagram to show you that, you know, anyway, I might be a nerd, but I think this was really, really cool. So for what that's worth, that's stress wave testing in a nutshell. Okay, so the trombone clamp, the panel clamp, the stress wave hammer, right, are all, you know, the instruments that we use that can kind of measure that signal, and then we correlate that signal with, you know, what we would constitute as sound lumber, all the way to there being no lumber there at all, completely hollow, a void, a cavity, you know. So, you know, the device isn't telling me you have a hollow post. The device is telling me that your impact, or the time it's taking from this signal to this signal, is extended, right? So it's up to us to assess these numbers, right, and correlate it to what we're looking at here, which is, you know, a severely damaged post. But yeah, I guess that's the lesson of the day, is that these instruments, these devices, you know, it's the information that you take from them, their output, that you have to put together and analyze and you know, use it in your tool bag, right, to help make a point or reinforce an assumption. So before we break out, you know, some of the different technologies that we use, you know, that are more non-invasive. I mean, really the ultimate one, the most cheap one, right, is what we call sounding, right? I've heard Jens call it the watermelon test, right? Where you're literally knocking using your hand or using, you know, a blunt object or a hammer, not beating on it, but just tapping and listening for that hollow sound, right? That's a good indicator of, you know, you're going to see damage. So we'll look at a beam, we'll see checking, we'll see some staining coming off of there, and it goes, you know what? And then start tapping on it. And that's known, that's a technical term. It's called sounding. And that is what it is. You're basically tapping on it and listening to the sound you hear. And by putting that together, if you've done enough of them, you can kind of feel, you can hear where follow the damage, right? Where it's going to be a fair amount of the time. So like I said, the number one tool, right? Your eyes, your ears, maybe you can smell it and taste it. I don't know. I'm not that good, but sounding, right? That's a good indicator. So then we talked about stress wave testing, pretty technical stuff. We're doing accelerometer here. We're measuring the distance across and, correlating that and graphing it. It's painting a picture. Another method, right, is called resistance drilling. Okay. Now, essentially what the person is doing. So in a sense, the technician has a really cool device that basically fits itself onto your typical cordless drill. Okay. And what they're doing is, the consultant or the engineer is basically going to identify some locations on the beam where they would like this resistance drilling performed, probably in the middle span of the beam. That's usually the area where the most deflection, right, where the loads are the greatest. The beam is working the hardest, so at the top edge of the beam, that would be the compression area of the beam. The bottom edge of the beam, that would be the tension face of the beam. So we have some systematic locations where we want them to perform this resistance drilling, and then that's what they do. And so basically, we see the guys on the ladder, and there's some locations marked out. Here's a point A. You can kind of see a little blip, and basically he's literally just standing there drilling, and a small spade bit is working its way through. And this thing is actually graphing the resistance of that beam real time. And it's charting it on the back of this device. So we're going to look at that right now. And it's really similar to like if you were looking at like a heart rhythm or like a lie detector test, like how that thing is just moving across the paper in real time. And it's just creating this long tab of a graph, right? So as he works through this material, he can then come down and basically, you would think it would be electronic or something like that, but it's a pencil, and it's actually measuring the resistance on a scroll of paper inside of this device. So let's take a closer look, and then you can literally see as he was drilling through, right? And you're working through the thickness. So he went through a 6-inch member, right? And basically notice the big dip or the deviation in the center, right? Which would indicate that the resistance, we're resisting, and then whoosh, there's just this big void. And that's what we're trying to see with the resistance drill. If we cut this beam in half, right, we're going to see probably a hollow section in the middle because there's no resistance there. There's nothing to resist that drill as it drills through the wood. So, this device, we use this in a series of locations across the property and utilize some of this data that the instrument gives us to then, put our best foot forward. Hey, maybe we actually really do want to cut into these beams, but we're not randomly just cutting into a beam because we know that then the resistance drill, picked up this big void, right? So in a nutshell, by no means am I an expert on resistance drilling, but that's a conceptual view of some of the other tools that we can use to help us make a more informed decision. Or conclusion, if you will. And so, these are samples that we were able to take back. So, the cat's out of the bag, right? But some of the indicators, right, of what might constitute damage, we see, some of these lines here, these checks in the beam, we see the staining coming out, the discoloration. Those are all indicators that we would want to, perform some resistance drilling or stress wave testing, or certainly poke and prod at it. Maybe not necessarily cut the thing in half, but if I'm walking through a job site and I see this, that's an indicator to go over and take a closer look. Let's sniff a little bit harder. So, as we, we can jab at it. Look, there's the pen, right? And he's gonna feel it. He might even break out a pocket knife or something like that and just give it a little jab, and it still feels solid. He's sounding, right? There's a sounding, knocking on it. Does it sound hollow? Sometimes it does. Sometimes it doesn't. You never know. You know, wood's different. It's organic. It's got a different grain. Every tree grows differently, right? So there are species, but you know, this isn't a composite material, right? It's organic. We're jabbing at it. It's solid. Look, his probe isn't just sinking in there, you know. So that's where we utilize, you know, these kind of instruments, or, you know, these kind of instruments to basically help us determine, you know, before we just saw the thing off of the chainsaw. So, and then as we can see, you know, the cat's out of the bag, but you know, the most economical probe you can use, it's a G2 pen.
Edge perimeter. This is where the pressure treating soaks in. You can see those knife marks, and that's where the chemical soaks into this outer ring. So you have this nice hard shell, if you will, but then you've got just a totally soft.
There it is.
Totally soft inside. It's like a custard-filled donut. That's that end. Then we go around to this side, and you can kind of see the same thing. Oh, you can see the water.
The juice.
Check out the juice. So this is that brown juice coming out that we were first looking at on the edge of the beam. And so again, if I can stick a pen through this thing, that's not a great thing. So
yeah, stick around for live Q&A at the end. We'll answer as many questions as we can in the hour, and then add the rest to the next show. So if you have a more specific question, stay tuned for a link to the schedule. You can schedule a free one-on-one call with me. Brooke's going to be monitoring the chat. I'm going to go through the Q&A panel at the end of the show. So be sure to ask us your questions.
Hey, good job, James. That's a lot of information. I feel like an engineer myself. To going through all the stress wave testing, and the sounding is my favorite. So I actually wanted to start with a story on that, because this happened long before we had stress wave testing and we had the drill resistance testing. About 8 years ago, we were completing a project and I was doing the final walkthrough with the client, and we were focused on signing off, and we had the client and the contractor were wrapping some things up. And the client said, "Man, I'm so glad you guys are about done. This has been a long project. There's been a lot of work. You know, it's been expensive. We're getting all these decks fixed, and just wanted to thank you for a good job. And I'm really glad you're almost done." And I turned to the client and I said, "Until we've gotten off the job site, until we've fixed all the things, you shouldn't say that." So I knocked on a post. I now know I was sounding. And I didn't think I was superstitious, but I might be now. Because I knocked on that post and it made a very unique sound. And I turned to the client and I turned to the contractor and I said, "Will somebody check this for me?" So we didn't have the cool tools out on the middle of this job site. So they just drilled a hole for me. And just like you were showing in the videos, nice piece of pressure treated. This was actually the beam on top of the post. You can see where we did our exploratory. We're going to try and look inside, see if there's something going on. That's what we discovered. I'm really glad we did, because this is one of those crucial elements that support walkways, that support decks. And the rest of it is floating around my office still, because it's been in here for about 8 years, because it's just kind of a really cool tool to show. You can see where the pressure treating goes in, where it's not, and you can see all the way through that. So what's the most practical way for you, James, when you're out on site? Is it to bring the equipment out? Is it to sound? What's the most practical thing for you to do to investigate these posts and beams?
I mean, you know, the cheapest tools we have, right? Our eyes and our ears, and just the knowledge that we've acquired over the years. Starting there, you know, that and just very primitive, you know, probing tools. But yeah, we normally don't show up with, you know, aside from maybe some moisture meters and things like that, just to help. It's really the educated eye, you know, at first, and never doubt. I mean, I say the eye, but then I always have that probe in my hand, and no matter where I'm walking, I'm touching and I'm feeling, because like you said, there are those times where it's like, this thing looks spot on. I'm just going to move on to the next one. And then sure enough, lo and behold, you bury that screwdriver 3 inches into the base of a post, and whoa, document that. So, you know, we do the best we can to be as thorough as we can, but we have a lot of ground to cover. So these visual observations, which is where we start, you know, we use our knowledge, we use our experience, but, you know, we're not superhumans, right? So I think it's virtually impossible to see it all, but we see enough to make a good assumption, and I like to think our win ratio is pretty good. So how about you guys? I know everybody has a different style. We're not all the same, you know, but that's, you know, I was in construction for a long time, so I kind of have that eye. I'm always looking at framing things, but I mean, siding, windows, there's little indicators, you know, everybody has a different style. So it's always nice to shadow our team members to learn little tips and tricks. So, yeah.
You showed it a few times in the video. It's seeing that color change in materials. So seeing something like the tannins or the oils from the wood coming to the outside, whether it's a post, a beam, behind some cladding, in a soffit. When you see those colors start to change, there's an organic breakdown that's occurring. And the materials are being displaced. And that's kind of one of those, really should look into this a little bit more and figure out not only what the issue is, but what's the causation. Ultimately, it's a causation. We got to fix that so this doesn't happen again. One of the common things that I saw in the presentation, the video, looking at this piece and these extra posts that are sitting back here behind me, they're all missing the middle. Can you explain from a engineering standpoint, one, the impact of that, missing the core of your wood, but from a waterproofing standpoint, how does that get there?
Yeah. I mean, obviously, you know, missing the core of something, like we depend on that entire cross-sectional area of that member, 100% of it, right, to support the loads that it was intended to support. So when we start decreasing that cross-sectional area, I mean, you can take a big 6x12 beam, right, and it might only have the structural integrity of a 4x4 or 4x8 or 4x6 now. So aside from just the decrease in that cross-sectional area, how does the water get there? Wood is porous, right? Wood is an organic material. So no matter how many chemicals or, you know, the natural tannic acids that are designed, you know, cedar, redwood, these things that have those natural tannic acid that like are weather resistant. There's really no tried and true method. All wood is going to absorb water, whether it's capillary action from sucking it through its end drains like a straw, or just being exposed, right? Sitting there over time with a flat member, looking up at the sky and just getting wet. So yeah, I mean, weatherization, protecting it, shedding the bulk water. Maybe we can't keep all the water out. We can design to let water in, but we're going to let it get out. We're going to design it to be able to not hold on to that water, but to allow it to drain through. So with good weatherization, with good materials, you know, you're never 100% foolproof. But you know, you get pretty darn close. So yeah, I have a feeling we're getting close on time. I don't know. Is there any questions or from other than Jim? Darn it. Love you, Jim.
One of the big things that I've noticed with these posts and beams, though, is when they're brought from a factory, and we'll call it pressure treated, preservative treated, they're treated in some fashion. And we know that the treatment process only goes in so far into a piece of wood. And if you order a 12-foot piece and you need 11 feet 8 inches, inevitably you have to cut off an area. So now you've got exposed end grains. And so that's what we're seeing with this piece that I shared, and a couple of those pieces that were in your segment. They were probably cut in the field, and those end grains weren't protected, and because of that, water got into that core. And over time, the wood tries to go back to its original state of soil. Hey, well.
So David has a question in the chat. He says, can the infrared camera assist in detecting voids in beams and posts? So
the short answer on that is probably not. the infrared camera senses thermal anomalies, so temperature variations. And it may be kind of tough to see a temperature variation in a post or a beam. Not saying it's impossible, but it's really not designed for that purpose. If you had, for example, a piece of wood that was water saturated, is it a warm day or is it a cold day? And then do you have any sort of temperature changes on the surface of that could affect it? So it doesn't see into things, the thermal camera, but it sees what's being transmitted through things. So if the internal temperature of the wood is super cold because it's wet, it's probably going to transfer to the outside and we're not going to see that cross section. But certainly if you sense something, even with the thermal camera, first we probe the exterior of it, and then I knock on it. Because we don't oftentimes have all the tools out there. Good question though. Any others? Okay, well, first off, we want to appreciate everybody for being here today. Make sure that you're all well aware we have a ton of free resources. We think information is key, and sharing that information is very important to what we do. It's information, it's education. As we learn it, we want to share it with other people. So we have a ton of resources for boards and managers. Go to our website, j2consultants.com/resources. You can find a lot of information there. You can catch every one of these podcasts. I know that the regular building doctor, I'm sure, is going to return here shortly. I believe he's going to be on next month with our very own Ken Waldall to talk about landscaping, because Ken is a landscape architect and April showers will bring those May flowers. So it's a good time to start talking about that. Want to thank you all. Have a great week. Thanks for being here.
Thanks, guys. Appreciate it.